Hi, I'm Santiago.
I'm Max.
I'm Carlos.
And I am Andres.
And today we're going to present our range of volcano project.
Our solution for the problematic.
So our company, we here at Volcanism are very passionate about harnessing the power of technology and bring the dynamics of nature into life. So our company specializes in the volcanic activity with precision and offering state-of-the-art tools for research, education, and hazard management. So here at Volcanism, we predict, we prepare, and we prevail.
Here's the introduction or what we were hired to do. First, our objective is to simulate the eruption of the Popocatépetl volcano and determine a safe radius where the stones will not fall. So here's a little bit of context. The Popocatépetl is an active volcano, and understanding the behavior of the falling debris in an eruption is crucial for danger mitigation. So why is it important? Our study can help define safety zones around the volcano to protect communities from the falling debris. Here's a little bit of context about the Popocatépetl. So it has a height of 5,452 meters above the sea level, but 3,032 meters above the ground. The crater of the volcano has a diameter of 900 meters, and the debris of the volcano can reach speeds up to 100 meters per second or more.
So now, why simulate the eruption? Well, there's three main reasons. First and foremost, I'm sure you both know the famous words, safety first, right? So by simulating the eruption, we can calculate where the stones will fall and therefore establish a radius that will protect the people and as well as infrastructures. Now, data-driven approach, so we're gonna be using real data to simulate the rock trajectories using a physical model that accounts for drag and gravity. And then the volcanic risk, which is Popocatépetl is known for very frequent eruptions, and the debris can be ejected at high speeds, like my teammate said, of around 100 meters per second or even more. Now, defining the safe radius. The largest range, which is the largest distance at which a stone will define the maximum radius for the safety zone, and our recommendations based on our our program is that we recommend a safety zone of about 11,890 meters or 11 kilometers from the base of the volcano to ensure no stones will fall within the area.
But the question is why?
Now, with the formulas, how we did get this? We use mainly, two equations, development method, we use for X and for Y. Why we use development method? Because it's an equation that uses the position you are in the previous position to get the next position. And why this better than like the Euler method? It's more precise thanks to those two positions. For the formula
For formulas, we have the acceleration and velocity. First, acceleration with respect to distance, which is the derivative of velocity with respect to time. Here we have v, which is the drag coefficient, velocity, divided by mass. And for velocity with respect to position n, we have xn, which is the position of x, and xn minus 1, which is the position of x before xn. And delta t is time step.
Now for the development method for X, it's this equation, and I'm gonna present what's its value. Xn, like my partner said, it's the position, but the next position to xn 2 times the value of the position minus xn minus 1 the previous position. Then the sign. This is, if I'm not mistaken, for a Matlab function to determine the sign from the velocity, more or less. Then, this is just to help to be more accurate in the development method. And this part is like the most important for the development method, because while I was investigating, you only have like this part, but when you have the drag, you also add this part, because this is the equation of the velocity, but it's to the square, and you also have the drag coefficient, the v over the mass, but you square it because it's proportional. Well, I was mistaken to say like it's proportional this to the
these quantities that you have in red, what do they represent?
Oh, this is like the velocity xn. It's
no, in overall, like all of them together.
Oh, it's the, what I was investigating is
The drag.
the drag coefficient, yeah.
Yeah,
Oh,
no,
This is
no,
more of the drag.
Yeah, but in general, what it
The
is?
drag, yes. The
No,
drag.
it's the,
Yeah, you have it in a previous slide, right? Yeah, that one, right? No,
Is the VN.
The acceleration.
yeah, it's acceleration due
Ah,
to
yeah.
the or
It's the formula of the acceleration, but you do
yeah,
it
but
to the
it's
square.
instead yeah, because you were saying something about the sign. So here, instead of considering as an acceleration, like increases the velocity, we see it as a braking, like it breaks the projectile or whatever. I mean the rock. That's why you add the sign there.
Oh yeah, it's also here. It's a function in Matlab that helps us determine the direction of the velocity.
All right. Yeah, yeah, because you said something like to be more accurate, but I think that statement is a little bit.
the one half. Well, I was
You
investigating-
said the one
yeah,
half.
the one half
Yeah,
is
the
like
one
to be
half.
more accurate. That's why while I was investigating about well,
No, the one half comes from the
From the
from the
formula.
equation.
no, so because here you have the acceleration, right?
Yeah.
So everything that is in red is the acceleration.
Yeah.
So remember the case where
It's-
instead of having y,
It's from the formula, no?
Yeah.
Because it's
So-
the formula is also known as like the high school kind of formula says 1/2 acceleration time squared, no?
exactly. Yes.
That's where the 1/2 comes from that formula.
Yeah, it's not to be
It's-
more accurate.
well,
this
it's
this
It's just
form-
part of the formula.
Oh yeah.
It's part of the formula.
Well, but-
I mean,
well-
and this formula you reach when you have a constant acceleration, which is in this case the gravity, when you solve the equations of motion starting from the Newton's formula,
Yeah.
right? Yeah.
Yeah.
So yeah, that's why you get the 1/2.
Mhm.
Yes.
Oh,
So it's not to be more accurate.
Well, I was investigating like to be more precise, but that's why I said
no,
oh,
no,
so
it's
that's
not
wrong?
because of that. No.
Okay. Well, then the same.
Yeah,
This is the,
you can erase that 1/2 from there. It's not to
okay,
be
okay.
more accurate.
Then the velocity is times the square because I read that it's proportional to the drag. This is the v, that it's the damping constant divided by the mass, and then this ensures the change in position in Scalzo property. Can you? Then it's the same for y, except you have the minus g plus delta t squared, and this is for the object to accelerate downward, meaning that with this is the downward velocity will increase over time.
Gravity force.
Here's how to get V, the drag force, with this formula. First pair represents the air density, which can be calculated with the barometric formula, or the ideal gas law, which at 5,426 meters is approximately 0.75 kilograms per cubic meter. Then the CD represents the drag coefficient, which for spherical ashes, it is a constant of 0.47, and the area transversal is basically the cross-sectional area of the ejected ash, which is spherical, and it's calculated with this formula. And it is assuming that an ash is 1 millimeter in diameter, basically. So that would be the
Now for explaining our code and how we did our integration. First we have the main file, which is what runs everything. And at first we have the function of the main file, which we simulate the parameters, which is the first 3 parameters, which is the number of trajectories you want to input into the code. And then the time steps, which we chose was 1 second. And the total time of the entire simulation, which we chose was 1,000 seconds. Then we have to plot all these trajectories, so we start on by a figure which opens up a graph, then hold on to keep all the plots inside the graph, read on to make it a little bit more aesthetically pleasing to the eye and easier to read, and then just label the X and Y positions as well as the title, and then keep the lines with this line kind of format, and then put in the volcano graph. Then we have this, which is the colors, which pretty much creates so that each different trajectory gets a distinct color. And then the distances, which we get an array of zeros in order to store the values of each trajectory, of the number of trajectories, which in this case is 15. And then we store that into the distances variable.
Here we have a for loop that it's going to store in the distances. Then from 1 to the number of trajectories that in our case was 15, and well, it's going to store it, it's going to end the loop. We have distances with an absolute function, because what happens is that, for example, if a rock can go to the right and another one can go to the left. The left, it takes the value as negative, so if the distance of the one from the left is greater than the one from the right, it wasn't counting it because it was negative. So you could have, for example, 2,000
Right,
positive
yeah.
and minus 3,000, but for the program, the
Yeah,
correct
it
one
will
was
be
2,000.
the one is bigger than minus 3,000, right? That's
Yes.
what you are saying. Yeah.
So, well, we have this, then we have the max distances to get the one that is the greatest.
All right,
And we bring it here, the longest trajectory, blah blah.
all right.
Now, here we have the function of the volcano, which basically what we did is we graph a horizontal line with the height of the volcano, which in our case is 3,033. And well, we graphed two functions to have the size of the volcano. And yeah, that's it for, well, we have R for color red and the line width so that the line is
Thick.
Yes. Next.
So now, the hard part, to calculate the trajectories. So to do this, we had to put the function of calculating the trajectory, which is delta time, and the total time and the colors. So for this, we need parameters, which is our mass, our drag coefficient, our gravity, and the number of steps we want to calculate. So then for that, we need to generate the initial conditions, which in this case is going to be our initial velocity that we said was going to be random because we don't know the probability of how the rocks are going to initiate in the initial velocity. So we set a parameter of around 100 to 300 for initial velocity, and it will choose a random value
So
and
you-
assign it to the trajectory.
I'm sorry to interrupt. So you said the minimum value is 100 and the maximum value
Well,
is 300?
Yes, because it said that it can reach a speed of 100, and like in searching about volcanoes, we came to the conclusion that it some cases have come to 300 meters per second.
Which
But,
is
do you think that the minimum velocity
no,
is
the
100?
minimum velocity should be 0, but for this case, we
It's-
implemented it to 100 in order to kind of calculate the greater distances of the more knownly or higher and faster velocity trajectories of the rocks.
Yeah, it can also
Yeah,
be
so you are trying to kind of simulate the worst case.
The worst
scenario.
case scenarios, yes,
exactly.
of course.
So we have the best.
The best safe radius we could implement for the people and for the safety.
It's better to have more than less.
Yeah. And then, of course, for the launch angles, as well random, it could be either from 0 to 180 degrees. It could go either way from the volcano. And then now the initial conditions, which we know they are our x position is going to be 0 because it's not moving. Our y initial is going to be 3,300, which is the height of the volcano. And then our velocity in x is going to be our initial velocity times the cosine of theta to get the initial velocity in the x, and then same for the y, but instead of cosine is sine. And then initialize the arrays in order to store the position. So to get the x position, we initialize an arrays of zeros in order to store the number of steps for both x and y positions, and as well as x1 and y positions, which will equal then to the x current and y current positions.
Right.
And then from there, we can set a new variable called the previous position in order to store the variables into the previous step. So then we put the x current and y current minus the velocity of x and y times the delta t, and then for y we also have to add the gravity and this dt squared.
Pause here. So
Yes.
maybe you're not talking too much. You're shy. So yep. Somehow it's weird. Yeah. So in this program, how can you kind of relate these names with the formula that you showed me in the previous
That's
slide?
why we're going to come here in our for loop.
Yeah, so for example, it's previous. Yeah, but I want him to answer that.
okay.
Yes.
Well, with this,
Yeah. So
with this,
no, the previous one.
The,
Previous.
no, the verde, I think.
Yes.
You mean?
Yeah, this one.
this one.
Naming here, naming wise. What's the translation in the program for yn plus 1, yn minus 1
In
in the program? Yes.
it was spur, right? Let me see the formula.
Yeah, probably I'm including you the 5 minutes of questions, so don't worry.
Oh, okay.
Yeah, no worries.
Here is well, here's for y, for x, but for example, here we have here we have both, like the current x minus the previous x, and the current y minus the previous y by distance,
So
Which is-
current means or stands for
which is the change in time, basically. Like, well, here's for y, but
no, but let's say forget about that part just for now. Yeah, I mean, because here you have some subscripts right here, n minus 1 and plus 1, right? So I want you to relate these. The first numbers that you have there. Yes. Yeah. So I want you to relate these subscripts with the naming that you use in the program.
which is
The variable.
yes, basically.
Yeah, because we did. I mean,
Basically, is the the
current means what?
which is the x.
Well, I mean here is bx, right?
Yeah, it's well, here you're using y, but it's like yn plus 1, right?
Which one?
The current y.
No.
No?
Does anyone know?
Yes. Go back to the code. So we have the previous, the current, and the next. So if you go back to the formula, we'll have the yeah, go back to the formula. We have this is the current, this is the previous, and this is the next. So
that's
it stores the number of the current one minus the one of the previous in order to calculate the next time
And
and
that's
then
going
each
to
step.
come in play in the loop of that it's going to use the Bartlett method
Yeah. Which is the next part of our of the code.
So
Yeah, I mean, with that I'm happy. You can skip that part of the code.
Okay.
we
Yeah,
have
you
the
can go.
Bartlett
You can go ahead with the simulation.
Okay.
All right.
Okay.
Well, but before, just keep going. on the
You
first page.
did this for the plot.
Yeah,
For
The real time.
Because
the
we have
preview.
like two, the one that calculates each point, and then when this finishes, we have like one we draw a line so that it's clear.
I see. Yeah. Okay.
Do you want? We can open the code. Yes.
Pero
Yeah.
just the final part of the. Well, yeah, no, let's run it.
Very good.
Little slow, but it'll get there.
I mean, and you can see that it has more shots to the right because like it's randomly the angle, so it's not like one and one. No, it's whatever
randomized, whatever
dot
the-
points,
It's more
like in a real
randomized.
volcano.
Mhm.
Yeah, very good.
And in the end, our code is going to show us the maximum range.
No, you can wait until it
In the
finishes.
show. Yeah.
Well,
So
and while it runs, I can,
you
can see
calculate the maximum range doing the absolute value, right? That's
Mhm. which is here.
It has it.
Yeah, I see it. I mean, it could be a little bit random, I think, to get the value that you said at the beginning that was close to, I
11
think,
kilometers.
12 or 11
Yeah,
kilometers.
11.8 kilometers.
Yeah, but I mean, this is not too far, right? Because
Yeah.
the only thing that.
Well, the reason we chose or we got the 11.8 kilometers is because we set in our thing for just a 300 meters per second trajectory, which is, from what we found from research, the absolute worst case rock could be launched. And for that reason, we chose, just in any case that were to happen again, keep it in mind and keep the radius safe.
Yeah,
Just to make sure there's
the
no
odds
accidents.
aren't very big, but it's better to prevent if that happens.
As our Logan says,
Very
prevent, prevail.
Yeah, I think we can finish now. I'm gonna put